Hi there, this is about identifying anyonic topological order in fractional quantum anomalous Hall systems. This is a review of a preprint we put on the archive a while back of the same title, which has meanwhile been featured at Quantum Zeitgeist. They put out a nice summary of it, which you can find online. So what's the fractional quantum Hall effect to start with, without the anomalous first? So these are electron gases that are somehow confined to essentially two-dimensional semiconductor materials, so to surfaces, which I'm going to call sigma 2 in the following, subject to a strong transverse magnetic field indicated by the field lines here. So the key point is that making it a fractional quantum Hall system means that this operates at a rational filling fraction of electrons per magnetic flux quanta. So for each electron in the simplest case, in the unit fraction case, there are exactly k flux quanta of this magnetic flux. On this backdrop of this fractional filling fraction, every surplus flux quantum plays a special role. So this is called a quasi-Holo vortex, because at least in the classical picture it creates a little vortex in the electron gas. And the remarkable thing is that these surplus magnetic flux quanta on the backdrop of the fractionally filled system, they are solitonic anyons. What does it mean? It means that as a pair of them is what's called braided around each other, or the world lines rather are braided around each other, the entire system picks up a phase vector, the quantum state picks up a phase vector, which depends only on the topology of this process, meaning only on the isotopy type of this process. So it doesn't depend on any wiggles in this path here, but only on the fact that these two surplus flux will end up being interchanged at the end. So in this sense, in this way, such a process is independent of little details and hence is noise resilient. That's a very important aspect for using such processes as topologically protected quantum gates. So the remarkable thing about quantum Hall systems is that they have actually been observed in experiment for a while now by a number of independent groups, which makes them stand out from other proposals for anyons which only exist on paper. Now, the anomalous Hall system was discovered, well, it was experimentally observed just very recently, predicted a while back. And here, the magnetic field is actually absent. That's why it's called anomalous. Somehow it shows a Hall effect without there actually being the magnetic field, which would seem to be so important for the effect. The point is that there's some intrinsic process in some intrinsic property in certain crystals called Berry curvature over the momentum space, which plays the role of flux and position space. In fact, there's a kind of duality between ordinary Hall systems of the form we've just seen and their anomalous counterparts, where position in the ordinary case gets replaced by momentum variables in the anomalous case, and the magnetic flux gets replaced by Berry curvature. So these things have been observed recently. Well, this anomalous Hall effect has. So that suggests that these systems are viable topological quantum hardware, and that it suggests that they also should exhibit some form of anyons. But the open question has been, where and how are anyons in fractional quantum anomalous Hall systems? There was no theory explaining how to even find, where to even look for them. So that's the question we're addressing here, theoretically. So the answer, we step back and ask, well, how do we generally identify anyonic ground states? Well, like this. So assume a crystal symmetry group G in the Bloch Hamiltonian space A. So a space of possible Hamiltonians per each momentum that your system can acquire in its given deformation class. That defines kind of in which context, which kind of systems we're looking at, and what kind of deformations of them we're allowing. Then topological phases of such crystalline materials are classified by this formula here, which I'll explain in a moment. So pi 0 of the mapping space of G equivalent maps from the torus to that Hamiltonian space. Let's unwind it. So map stands for the space of maps. Well, why is that? That's kind of the definition of a Bloch Hamiltonian by Bloch's theorem. The Hamiltonians in such a crystal, so the crystal structure is defined by a map that sends crystal momenta to Hamiltonian sort of internal degrees of freedoms of electrons of that momentum. So that's why we're looking at these maps. And because we have a crystal symmetry, these maps actually have to be equivariant. So that's the math jargon for this formula, which is the formula you will actually find in solid state texts, which says that the Bloch Hamiltonian at a transform momentum under some point group symmetry of the crystal gets conjugated by certain unity operators, which can also form a representation of that group. So in total, this is what in math you'd call an equivariance condition under the point group action on the crystal and this adjoint action on the bands. So that's why we're looking at equivariant maps. Here's the crystal symmetry, the band symmetry. Now, passing to connected components, that's the usual step of looking at the topological invariance. It means you look at the formation classes of such systems. You allow your system to continuously deform in its given class, which is determined by this nature of this space here. And taking the connected components, that means this is passing to the topological characteristic. So you allow continuous deformations of the system, but no non-continuous deformation, and so that makes it evolve in a certain realm. So, okay, so there's some extra remarks here, which I skip over for time reasons. So what does it now mean to have topological order? Well, we claim, and that's the main insight here, the main input, that means that our Hilbert space of ground states, of topological ground states, is a representation, irreducible if we're in some so-called selection sector, of the first fundamental group of that space. So here we had pi 0, and this is pi 1, the fundamental group of that space. So why is that? Let's ask, or let's step back and say, how does this come about? Well, this is by the topological version of the quantum adiabatic theorem, which says that gap ground state Hilbert spaces form what's called local systems of flat bundles over topological moduli space, over the space of external parameters. So suppose we're somewhere in our external parameters. So the external parameters here is the crystal structure embodied by the Bloch Hamiltonian. So it's a point in this mapping space, P1. So associated with that is a given Hilbert space of quantum ground states. But now the thing is, the quantum adiabatic theorem says that as we move along a path adiabatically, so slowly enough, of these external parameters, hence in our space of crystal configurations here, our ground states will transform along according to some unitary operation, some unitary operator. Such that as we keep going, there's another unitary operator, and there's compatibility conditions between these, which make this a flat connection, the parallel transport of a flat connection. But that means equivalently that these Hilbert spaces form a representation of the fundamental group at any base point C, so at any topological phase. That's how this formula comes about. Actually, more precisely, the ground state TQFT is generally covariant. So if we assume that we really do have, that's what we want to be discussing, that we really do have topological ground states, then they're expected to follow the rules of topological quantum field theory, and hence, as such, must be generally covariant, meaning that band topologies, or Bloch Hamiltonians, that differ only by diffeomorphisms of the base space, here the Brillouin torus, are equivalent as seen by their TQFT. So they might be classically distinguishable, but we're now asking how do our topological ground states discern these phases, and they will not actually distinguish, well, in some gauge theoretic sense, between diffeomorphism deformed phases as follows. So the topological phases as seen by the topological order will actually be the connected components, not quite of this mapping space we stated above here, but it's what's called its homotopy quotient by the diffeomorphism group, in this case the equivalent diffeomorphism group of our torus. And the topological order will then be pi 1 of that homotopy quotient. So this homotopy quotient is also known as the Borel construction. And pi 0, this effectively just amounts to forming the ordinary quotient of pi 0 of the original space by the mapping class group, the equivalent mapping class group of diffeos. Whereas for the topological order, it means essentially to form an extension of the group we had before by the mapping class group. So that's the abstract theory answer, really, in quite generally, for how to identify topological order in systems. So let's apply these formulas now to the case at hand of fractional quantum anomalous Hall systems in fractional Chern insulators. So these are generically two-band systems, and that's the case we'll be looking at, where the Bloch Hamiltonian hence takes values as a map from the Brillouin torus to 2x2 matrices, having two eigenvalues, the lower one being that of the valence band and the higher one that of the conduction band. So because it's 2x2 matrices, everything this is a standard story, can be expanded in Pauli matrices, which serves to show that the difference between the energy eigenvalues, these two eigenvalues that the Hamiltonian can have, is this formula here, and asking the system to be gapped is asking that expression to be positive, which then means that the valence bundle is then characterized as being the -1 eigenspace bundle of this normalized form of this Hamiltonian. If you look at these formulas, it's easy to see if you just sit down and look at them for a moment. You see that they are saying that the space, the Hamiltonian space of Bloch Hamiltonians, is a two-sphere in this case. Right? We have these three coefficients here. The sum of the squares of them is positive. After normalization, it's actually 1. That defines the sphere. So in this system, and this is well known. This is not new, but it's important. The band topologies are characterized by maps, continuous maps from the Brillouin torus to the two-sphere. So that's the situation that we are looking at. All right, so this means the valence bundle is some pullback here. I'll skip over this for time reasons. And the standard result is that topological phases are characterized by an integer, which we can either understand as pi0 of maps from T2 to S2, as we just argued. This is called the fragile band topology, because that's the topology of the actual system, the way it's set up. Whereas we can also allow the system to explore higher conduction bands, right? In the previous model, we just had modeled a single conduction bands, but of course in reality there are infinitely many unoccupied conduction bands. And if we allow the formation of the system to explore this space of higher conduction bands, we are asking for classification in the stabilization of the previous case in the stable band topology. And the interesting thing here is that in this case it makes no difference. By something called the Hopf degree theorem, these two integers we get actually the same, and hence they are known equivalent as the winding number or the Chern number. So fragile topology is the same as stable topology for topological phases of these two-band Chern insulators. But this is no longer the case, right? So this has, I think, tricked people in not paying enough attention to this fragile case here, because it sort of makes no difference on pi0. But we just saw that to get topological order into the picture, it actually, we don't just look at pi0, we look at higher homotopy groups of our space, in particular pi1. And on that, it makes a huge difference. And that's what we're going to see now. It makes actually the anion difference, whether we use the fragile or the stable topology. So a quick computation shows, this is some standard cohomology argument, that if we work with a stable topology, as before, so if we take our space of band Hamiltonians, or Bloch Hamiltonians to be BU1, then pi1, the monodromy of this mapping space, is actually an abelian group, ZMO2, which you can just understand as the algebra of observables of Wilson loop observables in abelian Maxwell theory. So these have one-dimensional irreps, and there's no topological order here. So in this, if you take our prescription for how to identify topological order and do it with the stable band topology, you see there just cannot be any topological order, any non-trivial topological order. But let's do this for the fragile band monodromy, which is the one that is actually determined by the system, where we saw the classifying space of the Bloch Hamiltonians is the two-sphere. Then, by an old result in algebraic topology, so somewhat deep computation, one finds that this algebra, this abelian algebra or group, gets deformed. A central generator is added into the picture, which deforms the commutator of these two Wilson loop observables, making them no longer commute, but pick up this phase difference. And that phase turns out to be exactly the phase that we saw at the beginning of the braiding phase of anions. So the group algebra of this is well known to be the algebra of Wilson loop observables in Chern-Simons theory, as opposed to Maxwell theory. And that is understood to be the standard algebra of observables for Anyonic topological order on the torus. So this is what in ordinary quantum Hall systems, if you open the textbooks on what describes their observables, their Anyonic observables on the torus, they'll give you this algebra. But now, interestingly, our torus now here, because it's still carrying this head, remember, this is to remind us that we're dealing with the Brillouin torus, not in real space, but this is a torus of momenta. So this analysis predicts that these anions that should be there in fractional quantum anomalous Hall systems, or could be there, they will be localized in momentum space, because it's the same for algebra of observables, but now in momentum space. But so far, this assumed that all symmetries have been broken, right? Remember, in the previous formulas I had G superscripts here to indicate that things had to respect crystal symmetries, whereas these formulas crucially kind of work in the case, or apply only in the case all symmetries are broken, that this G is absent. It's the trivial group. So let's see what happens as we allow some non-trivial crystalline symmetry here. So first of all, again, we go back to just the Chern phases, and apparently not even that has been computed before, the trivial one. So let's look at the special case, because there's too many cases to discuss. This one is interesting, crystalline P3 symmetry, ZMod3 rotation of the crystal lattice. Turns out the topological phases now are an integer, a Chern number, as you would expect from the standard story, which comes in multiples of 3, but there's a finite set of 4 sectors that gets adjoined to this. This seems to be a kind of result that has not been anticipated before. So the actual fragile topological phase of Chern insulators, in this case, they always have a Chern number and a further discrete indicator. So how does this come about? This turns out to be indicating where the fixed points go. So the high symmetry points in the crystal under G equivariance have to map to fixed points of our G action on the sphere. Remember, this was a sphere sort of band, degrees of freedom, if you wish. And under this equivariance formula, there will be a rotation action on the sphere, which fixes exactly 2 points. So each of the high symmetry points, of the fixed points on our torus, will have to map to one of these fixed poles and cannot move under continuous deformations because they're disjoint. So this gives a priori 8 ways of mapping 3 points to 2 points, but then quotienting out the diffeomorphism actually reduces it to 4. But now we can go further. We can compute also the topological order, computing pi1 of the corresponding space. It's very interesting that up to some abelian factor, we get the symmetric group on 3 elements arising here as the monodromy, which can be picked up by the topological order of the system. So this symmetric group in the computation reveals itself as being the group of braidings, if you will, of the 3 high symmetry points of the torus. So under equivalent diffeomorphisms of this equivalent torus, there can be, for instance, pi rotations here that fix this one point and kind of braid the other ones around it. It's not quite a braid group that appears, it's just a symmetric group, which of course receives a surjection from the braid group. And it's nevertheless, it's still a non-abelian group, and it would make what could be called parastatistical anyons out of these high symmetry points. So the analysis here shows that the moment you do have symmetry, then the high symmetry points act as defect anyons, parastatistical defect anyons. So this is the beginning of some computations one can do. There's many more examples here, but I want to be quick here, so let's conclude. So we've seen that fractional quantum anomalous topological order is theoretically seen in the monodromy of fragile band topology, a consequence ultimately of the quantum adiabatic theorem. This gives clear predictions of possible topological order in FQAH systems via computations, rigorous computations, and equivalent cohomotopy theory. So to recall, band topology is maps to Bloch Hamiltonian space A from our Brion torus. The topological phases are its components, connected components, and the topological order is the monodromy. And for fractional quantum anomalous churn insulators, this Hamiltonian space happens to be the 2 sphere for 2 band systems. And that comes with very special properties. It makes, in the case that all symmetries are broken, makes appear solitonic anyons in momentum space by this old formula from algebraic topology. And if there is crystal symmetry unbroken, then the solitonic anyons go away, but the formalism predicts the existence of defect anyons in momentum space of parastatistical nature. So these are tantalizing targets for experiment, and that's what I wanted to say. Thanks.